Hey there, students. Mr. Mechnick with a podcast on phase changes. That's it, phase changes. What does that mean? Well, it deals with the different phases of matter. So, as we know, the different phases are solids, liquid, gases, plasma, and that fifth state of matter called Bose-Einstein condensate, which we're not going to focus on today in the podcast on phase changes. But what we're going to emphasize is what happens when a solid goes to a liquid, or a liquid to a gas, or a gas to a solid, or gas to a plasma, and what are these phase changes actually called? How is energy related to all of these within that system that allows for a phase change to occur? Does energy have to be added? Does energy have to be removed? And this will help us describe and understand how a phase change occurs. So here's the names of all of these different phase changes. I would probably assume that most of you are familiar with the phase change going from a solid to a liquid, which is melting, and we're also probably very familiar with when we heat something up like a liquid and we get it to vaporize to a gas, we know that that's called vaporization. So some of the other ones that we need to be familiar with is when a liquid goes back to a solid. And again, fortunately, we all live in Wisconsin and we're familiar with that. So when the temperature starts to drop and that water up in our atmosphere cools and condenses to a point where it's below freezing, all of a sudden we start to see some solid precipitation falling here in Wisconsin. When the gas in our atmosphere starts to condense and the temperature lowers, we have what's called condensation, so we can go from a gas to a liquid. Sometimes we can actually go from a gas to a solid. This is called deposition. And then we also have examples where solid can go directly to a gas, which is called sublimation. And then finally, the last couple of phase changes that we're dealing with are going from a gas to a plasma. That's called ionization. And then the reverse process is called deionization. So in terms of the energy dynamics within a phase change, we should understand two terms, endothermic and exothermic. Endo prefix means within. It has to take heat into the system in order for that phase change to occur. Exothermic means that heat has to be released from the system and it can cause a phase change to occur. So let's think about going from a solid to a liquid. So when something melts, does the solid object have to absorb heat or does it have to release heat? Well, if you have an ice cube, in order for it to go to a liquid, it has to absorb heat. So it's an endothermic process. So if we look at liquid going to a gas, if we want to vaporize some water, again, we have to add heat to the system, and that's an endothermic process. All right, now let's think about going from a gas to a liquid. So during condensation, a gas would have to be cooled down. It would have to actually release heat, so it would have to be exothermic in order for that phase change to occur. Or the same thing, if we go from a liquid to a solid, the liquid has to be exothermic. It has to lose heat energy in order for those molecules to reform into a solid. So I would like you to fill out the chart that you have on your note sheet and be able to identify if deposition, if that's an exo or endothermic, and same with sublimation and ionization and deionization. So when we look at going from one state of matter to another, we can focus on that heat energy that's required. The heat energy is going to drive the phase change. And so when we look at the energy that's being put into the system, we can also relate it to the temperature of that solid, liquid, or a gas and how it might change from one phase to another. So if we look at this example, this is what we call a heating curve. So the solid object, if we start down here, is very organized. The molecules are tightly compacted together and they're vibrating. So they're always in motion. They always have energy. But as the energy of that system increases, the molecules will start vibrating faster and faster and faster. And it will get to a point where the temperature won't go up anymore, but the substance, the solid, will start to go through a phase change. It will melt. And as it melts, it absorbs more energy until all of that solid is now in a liquid state. So as that liquid then is gaining more energy, it's going to start warming up. The temperature of that liquid will increase. And we get to a point right here on the graph, which is known as the boiling point of that substance. So if this was a heating curve for H2O, we would be able to look and find out that that boiling point is 100 degrees Celsius or 212 degrees Fahrenheit. So then, if we kept heating up that water, if we had pure water and we kept heating it and we added more energy to it, we're not going to be able to get the temperature to go above 100 degrees Celsius because water has a boiling point of 100 degrees. And eventually, once all that water has absorbed so much energy, it would then turn all of those molecules into vapor. And so here we would have this state of matter that we would call a gas. And again, that gas can keep absorbing energy, and as it absorbs more energy, it would warm. So this is an example of a heating curve, and we will look at some heating curves in class of several different substances, not just water, but other objects, because all objects has a specific heating curve associated with it. We can also look at, well, let's focus on a cooling curve. So as the temperature of that substance drops, we can see when there's a phase change happening. So during this interval right here between 2 and 6 minutes, this is when the phase change occurs. So the phase change when we're cooling something and we go from a gas, this would be the liquid state down here, but this is when the object is starting to condense. So we have condensation occurring here. We notice that it takes some time for those molecules to rearrange themselves and become less energetic because we're removing heat from the system, and then eventually that solid would be, or that gas would become a liquid after it's all condensed into a liquid state. And then as the temperature keeps dropping and dropping and dropping, we are going to get to a point where that object would freeze. So this would represent the freezing point of the object, and here is when the object starts to fully get into a state of matter that we would identify as a solid. And then once it's at a solid, the temperature can keep dropping even more. So again, this is an example of a cooling curve, and you will become familiar with both heating and cooling curves for many different substances. And one of the properties that can be that describes all types of matter is what's called a colligative property. So a colligative property are these physical properties of a solution. So things like the vapor pressure, the boiling point, freezing point, osmotic pressure, these are examples of physical properties of some type of solution and how the number of particles, the solute particles in that solution, can affect these properties. So for instance, one of the things that we're going to look at in class is how does adding a solute affect the heating and cooling curve? So when you add salt to water, for instance, how does that affect the boiling point or the freezing point of that substance? What happens when you have pure water versus water with a solute in it? How does that affect it? So one of the things that we will find out is that when you add a solute to a solution, it makes the freezing point lower. So the material that we're dealing with will have a harder time going from a liquid to a solid state and reorganizing itself into this form, because the solute will start to interfere with the arrangement of those individual molecules or elements or compounds, and you end up lowering the freezing point when a solute is present. So this is known as the freezing point depression. And the opposite is true when we try to boil something with a solute. So if we have normal water without any solute in it, water molecules will boil at 100 degrees Celsius, and they'll exist as a liquid, and some of them will escape and exist as a gas. But when you add that solute to it, again, it makes it much more challenging for the water molecules to escape, because there is some attraction between the solute and the solvent. And because of those intermolecular attractions, it takes more energy to make the solvent be released into a gas state. So what we see is that it will take more energy, so the boiling point is actually elevated when a solvent contains a solute. So that's it for today's presentation. So hopefully you have enough information to complete the study guide that you were asked to complete with this assignment. And if you have any questions, please write them down and bring them to class tomorrow.